In this video, I'll be solving several radical equations algebraically. Here are some steps that you can follow when solving an equation that has a radical symbol in it. And just to make sure you know what a radical is, I've drawn one here. So the first thing we need to do is isolate the radical part of the equation, means get it by itself. So here is the radical part of my equation, and you notice that there are other terms on this side of the equation, meaning the plus 3. So according to the directions, we need to take this piece of the equation and move it to the other side of the equal sign so that the radical will be by itself or isolated. It also says sometimes you will have radicals on both sides. Since there's only one radical in this problem, that won't happen for us. So let me do the first step. Since the 3 is being added, I'm going to subtract 3 on both sides. 3 subtract 3 simplifies to be 0, and you don't need to write addition of 0. So I will be left with the square root of x on the left-hand side, and 19 minus 3 is 16. So I'm done with the first two steps. Step 3 says raise both sides of the equation to a power that will undo the radical. So quickly, let me point out that all radicals have what's called an index, and it's written right here. Now, if it's a square root, we don't write the index. It's assumed to be a 2. So notice there was no index here in the original problem. You are to assume that it was a square root, meaning the index is a 2. So in the directions where it says to raise to the second power to eliminate a square root, it's because the index is a 2, so we're going to raise both sides of this equation here to the second power. If my index was a 3, meaning cube root, I'd raise to the third power. So here's my problem. Radical x equals 16. I'm going to take the entire left-hand side of the equation and square it, and I will square the right-hand side. Since this is an index of 2, powers, that's this guy, are inverse operations of roots, which is this guy. So since they're both a 2, they will undo one another, and I will be left with just x. 16 squared can be done easily on the calculator by hitting the square key. That turns out to be 256. So I've actually done step 4 automatically. I've solved for the variable, which was x. Step 5 is a word of caution that you should check your answers, because sometimes even though you've done all the steps correctly, the solutions will not check, meaning they're not actually valid solutions. Let me check my solution. My answer is 256, so I'm going to take the original equation and replace x with 256 and see if I get a true statement. The square root of 256 should be 16 for the very reason I mentioned before, that powers and roots are inverse operations. So if you take 16 and raise to the second power, and then take that answer and take the second root or square root, you should get back to where you started, which was 16. So square root 256 is indeed 16. So if I write 16 here, you see that I get a true statement that 16 plus 3 is 19. So since that's a true statement, that means x equals 256 is the solution to this equation, and what's more, it's the only solution to this equation. Now let me tell you, the fact that this was a positive number here tells me that when we went from this step to this step and squared both sides, I was likely going to get a solution to the equation because this was positive. What happens is, if this comes out to be a negative number, even though you do these steps correctly, you produce a solution that doesn't actually work, which means it's not actually a solution. So in the case this comes out negative, following these directions will produce something that is not a solution, which necessitates that you check your answer. Let me show you an example why that's true. The issue is with step 3, raising both sides of an equation to a power. So for example, if you take something that is a true statement and square both sides, you end up with another true statement. And this is like the example we did before. But what can happen when you square both sides of an equation is you can actually start with a false statement, such as this one. Negative 3 is not equal to 3. That's a false statement. But if I was to raise both sides of the equation, as step 3 indicates, to the second power, I get that 9 is equal to 9, which is a true statement. So what you'll have is an equation that has no solution. It is false. But when you use step 3 and square both sides, you end up with something that appears to be true. This is why you have to check that solution to make sure that this situation did not happen. Let's do a few more problems. So here is the radical once again, and my job is to isolate that radical, which means I need to somehow deal with the 3 that's being multiplied and the subtract 5. Now you have a couple options in the order in which you take those numbers to the other side. But typically what's done, you do the operations in the reverse order of PEMDAS. Remember that PEMDAS is a rule that you use when you are evaluating an equation or an algebraic expression. When you're plugging a number in, you are to follow these rules of PEMDAS. When you solve an equation, typically we actually do the opposite of PEMDAS. So for example, to get rid of this 3, since it's being multiplied, I will have to divide by 3. This subtract 5, to take it to the other side, I have to do the inverse operation of subtraction, which is addition, so I need to add 5. So it turns out you can do it in any order you want, but typically, to avoid fractions, you will do the reverse order. Normally with PEMDAS, you would say division comes before addition, but I'm actually going to go in the opposite order of that. I'm going to do my addition first and add 5 to both sides of the equation. Doing that is going to leave me with negative 5 plus 5 is 0 on the left-hand side. We don't write addition as 0. 22 plus 5 is 27. Now that I've done that, since the 3 is being multiplied, I will divide both sides by 3. I will be left with 3 divided by 3 is 1, and we don't need to write the 1. And 27 divided by 3 is 9. Here we're at that part where I have square root of x equals a positive number, so I think my answers will be fine. I'm going to check it anyway. But the fact this is positive leads me to believe that when I square both sides of the equation, I will get a result that is a valid solution. So this is where I'm at, and I'm going to raise both sides to the second power. And powers and roots are inverse operations, so this will simplify out to be x. And 9 times 9 is 81. This is where I need to check it. So let me erase everything I did. So now I'm going to check my answer. I take the original equation where I see the variable x, I replace it with 81 to see if it's going to work. And I notice that the square root of 81 is 9. And like I said before, if you're not solving an equation, you already use the rules of PEMDAS. So I'm going to do my multiplication before I do my subtraction. 3 times 9 is 27, and since 27 minus 5 is indeed 22, this is a true statement, which means that the result I got from this algebraic process is actually a true solution. Let me do a few more. So this one's going to be a little bit more complicated, and we'll show off more a little bit of step 4. So here is the radical part of my equation, and I need to isolate that radical part. We won't have radicals on both sides, so I can ignore step 2 for this problem. So doing step 1 to isolate that, again, I'm going to go against the rules of PEMDAS because I'm solving an equation. This is a positive 1, so I will subtract the 1. So subtracting 1 on both sides of the equation leaves me with 1 subtract 1 is 0. We don't write addition of 0. And 16 minus 1 is 15. Now I point out since the 5 is being multiplied, I will divide both sides by 5. 5 divided by 5 is 1, and like I said before, you could write 1 times this radical, but we typically leave that off. 15 divided by 5 is 3, so now if you notice, I've isolated the radical part of the equation. This is the part of the equation I needed to get by itself. So that means I'm on step 3. This is the part where I argued that since the index on a square root is a 2, that I need to raise both sides of the equation to the second power. So a radical with an index of 2 and a power of 2 will simplify out, leaving me with 1 minus 2x. Whatever is under the radical, often called the radicand, is the only thing that survives that squaring process. And on the right hand side I get that 3 squared would be 3 times 3 or 9. So I've raised both sides of the equation to that power. That means I'm on step 4. This is the first example where step 4 wasn't automatically done for me. I had to solve for the variable. This is just a linear equation, and I eventually had to subtract the 1 and divide by negative 2. And since I'm still solving, again, I'm going to go in the reverse order of PEMDAS. I'm going to do my subtraction first, then my division. So since this is a positive 1, I'm going to subtract 1 on both sides. 1 minus 1 is 0, leaving me with negative 2x on the left-hand side. And 9 minus 1 is 8 on the right-hand side. Finally, I do my division. The negative 2 is being multiplied, so I will divide both sides by negative 2. Negative 2 divided by negative 2 is 1, so I have 1 times x on the left-hand side, which is just x. And 8 divided by negative 2 is negative 4. Now my thinking on this was this step right here, when I got rid of the radical, happened where I had a positive number on this side of the equation. So I'm guessing that as long as I did everything correct, this result of negative 4 will be a solution to my equation. So to check my result of x equals negative 4, I'm simply going to replace x with negative 4. So here's the variable x, I replace it with negative 4, and now I just simplify the left-hand side to see if it simplifies down to be 16. So because I'm not solving an equation, I am just simplifying this arithmetic expression on the left-hand side. I do follow the order of PEMDAS. So for example, this radical here has an implied set of parentheses in it, so that would be the p in PEMDAS. I'm going to do whatever's under the radical first. But then within the radical I have subtraction, multiplication. So I'm going to do the multiplication before I do the subtraction. Negative 2 times negative 4 is positive 8. So when I replace this with positive 8, I'm left with this. 1 plus 8 is 9, so I'm left with the square root of 9 here. The square root of 9 is 3, so this would be nothing more than 5 times 3. And then since 5 times 3 is 15, I'm left with 1 plus 15 equals 16. If you want, you can actually finish that off and say 16 equals 16, which is a true statement, which means our result of x equals negative 4 is a solution to the equation. Let me do one more example that involves a square root. I will start like I did all the others by isolating the radical part of the equation on the left-hand side. That's this piece. The only thing on the left-hand side of the equation besides that radical is addition of 8. So I will start just by subtracting 8 on both sides. 8 minus 8 is 0, so that simplifies out on the left-hand side. I'm left with square root x minus 11 equals negative 2. This is an issue. At the beginning of the video, I talked about how when you square a negative, that process can sometimes take false statements and make it true. So I'm guessing this may be a problem in this example. Let's see how it plays out. Just like before, since the index on a square root is a 2, it's the only radical for which we do not write the index. I will raise both sides of the equations to a power of 2 because roots and powers do undo each other as long as they are the same number. This is a root of 2 and this is a power of 2. They will simplify out, leaving me with just the radicand, which is the stuff under the radical, x minus 11. So I'm going to copy down my radicand, x minus 11, and on the right hand side, negative 2 squared means negative 2 times negative 2, which gives me positive 4. And I'll finish solving by adding 11 to both sides of the equation. Negative 11 plus 11 is 0, so it simplifies out. We don't write add 0. 4 plus 11 is 15, so this is the result I get. So when this says not all solutions obtained will check properly in an equation, probably be better to think of as not all results will check, because it indeed isn't a solution in the first place. And I will show that now. So here I go to check my result, or my proposed solution. I replace x with 15 and see if this comes out to be 6. 15 minus 11 is 4, so I'm left with square root of 4 here. The square root of 4 is 2. On the left hand side I get that 8 plus 2 is 10, and on the right hand side I get just 6. This is obviously a false statement. You can skip this part of the video, but sometimes I like to share with my students things that I've explored when I was a student myself. When I was a student, I wanted to know why this algebraic process would give me a result that isn't indeed a solution. And I noticed that if you back the video up, we had a step that looked like this. In fact, this is what we got when we simply subtracted the 8 over. 6 subtract 8 is negative 2. If you look at this statement and plug in our proposed solution of 15 and investigate what happens, you'll see what went wrong in this process. On the left hand side you get the square root of 4. On the right hand side you get negative 2. This is what our statement was a few minutes ago for that x value. So if you think about this, this here is a false statement because the square root of 4 is 2. And that is certainly not the same thing as negative 2. But if you remember the very next step that we did when we had this a few minutes ago in the video, the very next step was to square both sides. So for that x value of 15, we actually were taking this statement down here and squaring both sides. And when you do that, this is what happens. You take that false statement here, right? We just proved it's false over here. And when you square both sides, the radical and the square cancel, you get 4. Negative 2 squared is negative 2 times negative 2, which is 4. I basically took a false statement here, and by squaring both sides, turned it into a true statement, leading us to believe that that result that we got, x equals 15, would be a solution when we just showed that it is not. So I think we've done enough of square roots now. Let me do a couple problems where we do an equation whose index is bigger than 2. So I hope to persuade you that even though we have a problem where the index is bigger than 2, it's a 3 now, we call that a cube root, that the directions play out very similarly. So for example, I'm going to isolate the radical part of the equation. Even though this is a cube root instead of a square root, we still call it a radical. The only thing on the left-hand side besides that radical is the subtract 4. So to isolate this, I would just add 4 on both sides of the equation. So on the left-hand side, I will be left with just the cube root of my radicand of 3x plus 7. Minus 4 plus 4 simplifies out as being plus 0. We don't need to write that. And 6 plus 4 is 10. So that's step 1. Step 2 says sometimes you'll have radicals on both sides. I'm not doing any examples like that. Step 3 says raise both sides to a power that will undo basically this radical. So since this is an index of 3, I will have to cube or raise to the third power on both sides to undo the cube root. So here goes. To undo the cube root, you will have to raise to the third power, and since I raised the entire left-hand side of the equation to the third power, I must raise the right-hand side to the third power. So you can think of it as this cube root of 3 and the cubing process simplify out, leaving with just the radicand, the stuff under the radical, 3x plus 7. So I'm just going to write 3x plus 7. And 10 cubed is 10 times 10 times 10, which comes out to be 1,000. Now I just have a linear equation. Again, since we're not simplifying, we are solving, I do the reverse order of operations here. The 3 is being multiplied, I will have to divide by 3. The 7 is being added, I will eventually have to subtract 7. Not that you have to do it in this order, but to avoid fractions, what's typically done is we do PEMDAS in the reverse order. So I'm going to do my subtraction before my division. So let me subtract 7 on both sides. Plus 7 and minus 7 is 0, so I will left with just 3x on the left-hand side. And 1,000 minus 7 is 993. I do that quickly in my head by just asking myself what 10 minus 7 would be. That's 3. Now, since the 3 is being multiplied, I divide both sides by 3. 3 divided by 3 is 1. We don't write 1x, we just write x. And since 3 divides into this evenly, I don't need a calculator. I know 3 goes into 9 3 times, 3 goes into this 9 3 times, and 3 goes into 3 once. So take your calculator, divide that out if you must, but I'm getting a result of 331. I believe it's a solution. So back over here, I'm going to write out my entire original equation, cube root, 3 times x. I'm suggesting that x should be 331 to make this equation a true statement. Now we have to be careful, the subtract 4 is on the outside of the radical. So here I am just checking my solution. This is step 5, check your answer. So here goes, 3 times 331 would be this 993 here. 993 plus 7 is 1,000. The cube root of 1,000 is 10. If you want me to verify that on a calculator, I can press Math, go down to the cube root option, and ask the calculator what number has the property that if I multiply by itself 3 times, I get 1,000, and it tells me the number 10 would be such a number. So this guy here simplifies down to be 10, leaving me with the statement that 10 subtract 4 is 6, which is clearly a true statement because 10 minus 4 is indeed 6. Since my result yields a true statement when I substitute it into the original equation, I'm going to call that result a solution. So x equals 331 does check as a valid solution. So I think if you have the patience, I have one more example that I'm going to do. So just to be thorough, I want to make sure that you see that this process works for any index, not just 2 or 3. So I'm going to do one where the index is a 5. It starts out much like everything else did in this video. We isolate the part of the equation that has the radical symbol. So to get rid of the 11 and take it to the other side, so to speak, I will do the inverse operation of addition, which is subtraction. When I subtract 11 on both sides, I get that the fifth root of x minus 5 plus 0 is equal to 9 subtract 11 is negative 2. Now earlier in the video I mentioned that you have to have caution when that comes out to be negative, but it turns out since my index is odd, we don't have the same problem as we did earlier in the video. But I'm going to just keep going through the steps here. I've done step 1, I've isolated the radical part. we don't have radicals on both sides, I'm going to raise both sides of the equation to the fifth power since this index on the radical is a 5. So let me copy this and do just that. I'm going to raise the left-hand side to the fifth power, and I'm going to raise the entire right-hand side to the fifth power. The fifth power and the fifth root will cancel, leaving with just the radicand, x minus 5. On the right-hand side, you have to figure out what negative 2 multiplied by itself 5 times is. I know an odd number of negatives gives a negative, and 2 to the fifth power is 32. So now I need to do step 4, which is solve for the variable. Since x isn't by itself over here, technically we have some solving to do. There's a minus 5, so we'll do the inverse operation, which is adding 5. And I get that negative 32 plus 5 is negative 27. So I'm going to back up and plug it in and see what happens. So let me take my original equation and replace x with the result that we got, which was negative 27. Now earlier in the video, I mentioned when we had a radical equals to a negative, that could create some issues. I think I even put a little sad face there. It turns out that was an issue because we had an even index. Notice what happens now that we're doing a very similar problem, at least we have a similar situation, with an odd power. Even though that situation happened, we get here that this simplifies out to be negative 32. Fifth root of negative 32 plus 11 equals 9. The fifth root of negative 32 asks the question, what number do I multiply by itself, fill in the blanks, 5 times to get a result of negative 32? And it turns out that the number negative 2 is the answer to that. The reason I know, if you multiply negative 2 by itself 5 times, you do indeed get 32. And that means the fifth root of negative 32 is negative 2. So to show how to do this on the calculator, if I press the number 5, the math key, and then option 5, this shows up cleanly on my calculator as fifth root because I happen to be in what's called math print mode. If I press mode on my calculator, I see that I'm in math print mode, not classic. Let me hit clear to go back to the home screen. Inside the radical, let me type negative 32, just to make sure you see that the fifth root of negative 32 is indeed negative 2. So, now that we've verified that multiple ways, we have negative 2 plus 11 is equal to 9, and negative 2 plus 11 is indeed 9. So my result of doing that algebraic process this time was plugged into the original equation and it yielded a true statement, meaning this result is indeed a solution. So hopefully with those examples, I've been thorough enough to show how these directions play out.